All right, so we're going to start chapter 10. In the previous chapters, we looked at uh, confidence intervals and significance tests. For example, we looked at a one proportion Z interval and a one sample T interval, and we looked at significance tests for categorical data, which we call proportion, or quantitative data, which we called means. So we did like a one sample T test or a one proportion Z test. Well, what if we want to test or come up with intervals to compare two proportions or two means? So that's what this chapter is all about, is comparing two populations or two treatments. So we're going to look at what we're going to call two proportion Z tests, two proportion Z intervals. So basically the process is the same. We're going to explain what's this problem about. So we're going to define the parameters, and then we're going to check to make sure that it's okay that we do it, check our conditions, and then we're going to do it, and then we're going to interpret it in context. So the four-step process is going to remain exactly the same. The only difference is now we're going to have two proportions. We're going to have two means. We're going to have two standard deviations. So the mechanics of making these intervals and conducting these significance tests is going to be slightly different. However, the process is going to be the same. Same four steps, just in how we check conditions, how we define parameters is slightly different from what we've done in the previous units. So let's get started by taking a look at proportions first. Okay, so we're going to look at two proportions. So for example, we have two populations or treatments, population one, treatment one, right? So 1, 1. Now, the parameter of interest, remember what we're doing in tests and intervals is we're trying to use the statistic, the sample, to answer the question about the entire population or the parameter. So here we're going to first concentrate on proportions. Remember, proportions go with categorical data. Do you fit into one of several categories? Okay, so we have two separate populations or treatments, 1, 2. Okay. The parameter of interest is P1 and P2. P1 would be the proportion of the population of females, for example, and P2 would be the proportion of the population of males. So the parameter is like before, the null and alternative must always be stated in the parameter, and we're going to try to use the statistic to answer the question about the parameter. So for population 1, we'll call its parameter P1. Population 2, we'll call its statistic P hat 1, and N1 to denote the sample size of population 1. So you notice it's the same notation we used before, but now we have 1s and 2s because we're not dealing with just one proportion. We have 2 to take into account. So same for population 2. The parameter we're trying to estimate is P2. The statistic is P hat 2, and N2 is the sample size from population 2. Okay. So the sampling distribution of P hat 1 minus P hat 2. So what is the shape going to be? What is the center? What is the spread? Remember, distribution, we're describing numerically what's happening with this data set. So just like before, we have to choose an SRS. Absolutely has to be from an SRS. Otherwise, we cannot generalize our findings to the entire population. Okay. Now, the shape is going to be approximately normal. This is going to be extremely important for us because if the data is not normal, we can't use z-scores to find p-values and then therefore come to a conclusion like the previous units. Same here. All right. So is the data normal? Well, we saw before that proportions were normal if n times p and n times 1 minus p were both greater than or equal to 10. Well, now we have two proportions, so we have to do that check for both. So as you can see going through here, N1 times P1 has to be greater than or equal to 10, and N1 times P minus 1, and N2 times P2, and N2 times 1 minus P2 all have to be greater than or equal to 10. The book's going to talk about this as large counts. The large count condition gives us normality. If all of these values are greater than or equal to 10, then the data is normal. Now we know the shape. It's symmetrical. It's normal. Saying that it's normal is enough. A normal implies that it's symmetrical. But just because a data set is symmetrical does not imply that it is normal. The center, the mean. Well, how do I find the mean of p hat 1 minus p hat 2? Well, remember that the mean of p hat is just equal to p. If I were to take every single possible sample out there and average all those samples, it would give me the population parameter, p. So the mean of p hat 1 minus p hat 2 is just p hat 1 minus p hat 2. The standard deviation is the same as before. Remember, we would do the square root of p times 1 minus p over n. Well, now we're doing the square root of p1 times 1 minus p1 over n1 plus p2 times 1 minus p2 over n2. We're allowed to use this formula for standard deviation if the data is independent, meaning the population is at least 10 times the size of the sample. All right, let's put this to practice. Let's take a look at this example real quick. Your teacher brings 2 bags of Goldfish crackers to class. One bag has 25% red and bag 2 has 35% red. Each bag contains more than 1,000 crackers. Using a paper cup, your teacher takes an SRS, simple random sample, of 50 crackers from bag 1 and a separate SRS of 40 crackers from bag 2. Let p hat 1 minus p hat 2 be the difference in the sample proportion of these red crackers. What is the shape of the distribution and why? So is this data normal? Well, what we saw in the previous slide, if the data is normal, then what must be true? So part A, the shape of the distribution, is it normal? Well, if it's normal, then N1, so the first bag, N was 50, N2 was 40. P hat 1 was 25. That was the sample proportion in the first bag. P hat 2 was 35, the sample proportion in the second bag. Now, if this shape is normal, the shape of this sampling distribution is normal, then N1 times P hat 1 and N1 times 1 minus P hat 1 and N2 times P hat 2 and N2 times 1 minus P hat 2 must all be greater than or equal to 10. So I can do this. The 50 times 0.25, that's 12 and a half. 50 times 1 minus 0.25 is 37 and a half. 40 times 0.35, 40 times 0.35 is equal to 14. And 40 times 1 minus 0.35 is equal to 36. They're all greater than or equal to 10. So yes, the shape is approximately normal for question A. Question B wants us to find the mean of the sampling distribution. So here was A. Let's do B in red. B wants us to find the mean of the sampling distribution. Well, the mean of P hat 1 minus P hat 2 is just equal to P hat 1 minus P hat 2. So the mean of P hat 1 minus P hat 2 is going to be P hat 1, 20.25 minus P hat 2, 0.35. So it gives us a mean of negative 0.1. And then let's look at part C. So part C says calculate and interpret the standard deviation. Well, am I allowed to do this? Oh, am I allowed to calculate and interpret the standard deviation? Well, is there more? Is the population of goldfish in each bag larger than 10 times the size of the sample? So bag 1 we sampled 50 goldfish. 50 times 10 is 500. Are there more than 500 goldfish in the bag? And it says, yes, the bag contains more than 1,000. Let's look at N2. 40 times 10 equals 400. Are there more than 400 goldfish in the second bag? Yes, it says that there are 1,000. So we're allowed to use the formula for standard deviation. Well, how do we calculate the standard deviation for a two proportion? Well, remember the formula said that it was p hat 1 times 1 minus p hat 1 divided by N1. And in this case, N1 was 50 plus p hat 2 times 1 minus p hat 2 divided by N2. And take the square root of that. This will give us the standard deviation of p hat 1 minus p hat 2. So if I typed all that into my calculator and did all the work, I would get 0.0971. I'm not going to take the time right now to show all the strokes on the calculator. I think you guys can figure that out. So now, what do they mean by interpreting it? What does this number mean when they ask us to interpret this standard deviation? We always have to interpret in context of the problem. So what does that 0.0917 mean? That it's telling us that the difference so what did we do? Bag 1 minus bag 2. The difference between bag 1 and bag 2, on average, typically varies by about 0.0971 from the mean difference of negative 0.1. So on average, these samples will be approximately 9% away from the mean of negative 10%. Okay. So the sampling distribution, shape, center, spread, and interpret in context. What's the shape? It's normal, as you can see in blue up here. It's normal because N1 times P1 and N1 times 1 minus P hat 1 and N2 times P hat 2 and N2 times 1 minus P hat 2 are all greater than or equal to 10. Where's the center? Oh, about negative 0.1, because it's the difference between P hat 1 and P hat 2. What's the spread? Oh, about 0.091. What does that mean? Oh, on average of all of our samples, on average, the difference would be about 9.71% away from the mean of negative 10%.